Problem 2.8 goes like this. Which of the following arrangements of pin fins will give higher heat transfer rate from a hot surface? 6 fins of 10 centimeter length or 12 fins of 5 centimeter length. The base temperature of the fin is maintained at 200 degrees Celsius and the fin is exposed to a convection. This is convection, not conviction. Do not get convicted by this convection. Convection environment at 15 degrees Celsius with convection coefficient 25 watt per meter square degrees Celsius. Each fin has cross-sectional area of 2.5 square centimeter, perimeter 5 centimeter, and a material have thermal conductivity 250 watt per meter degree Celsius. Neglect the heat loss from the tip of the fin. Okay. So in this problem, basically, two cases are given, and you are supposed to calculate heat transfer rate from two arrangement of fins in case 1 and case 2. So let us, in order to solve the numerical, let us first draw the schematic. So in this problem, as you can see in case 1, there are 6 fins of 10 centimeter length connected to some base surface at temperature Ts, and they are exposed to the surrounding having temperature T infinity and convective heat transfer coefficient H. The cross section of the fin is circular because it is saying pin fin, and pin fins are nothing but cylindrical fins. So let's say their diameter is D. So this is case 1, where 6 fins of 10 centimeter lengths are connected to the base surface. In case 2, now fins of same diameter but 12 numbers are connected to the same base surface at temperature Ts, but their length is 5 centimeter now. Okay, so case number 2 is 12 fins of 5 centimeter length are connected to the same base surface. So you are supposed to calculate what will be heat transfer rate from this arrangement of the fin and heat transfer rate from second arrangement of the fin. Got it? 6 fins of 10 centimeter length, what will be the heat transfer rate from the base surface? 12 fins of 5 centimeter length, what will be the rate of heat transfer from base surface? Here base surface remains same in terms of geometry, in terms of surface temperature. Okay. After drawing this schematic, let us enlist the given parameters. So in case 1, the number of fins are 6 and the length of the fin is 10 centimeter, that is 0.10 meter. In case 2, number of fins N2 are 12 and their length is 5 centimeter, 0.05 meter. In both the cases, base surface temperature remains 200 degrees Celsius. The fins are exposed to the same environment at temperature 15 degrees Celsius. Convective heat transfer coefficient 25 watt per meter square degree Celsius. And all the fins in both the cases are made up of the same material having thermal conductivity 250 watt per meter degree Celsius. Cross-section, cross-sectional area of each fin in both the cases is 2.5 centimeter square, that is 2.5 into 10 to power minus 4 meter square, and perimeter is 5 centimeter, that is 0.05 meter. So only fins are varying in numbers only and length. Rest of the parameters remain same in both the cases. Now let us take some assumptions to solve this problem. So assumption number 1, we are going to consider one-dimensional steady state heat transfer. Assumption number 2, no heat generation within the fin itself, that is Qg will be 0. No thermal contact resistance between the base surface and fin root at the joint. That means this is called as a root and this is base surface temperature. So because of no thermal contact resistance between the joint between the base surface and root, temperature of the fin at the root will also be equal to Ts. That is 200 degrees Celsius. Assumption number 4, isotropic and homogeneous fin material. And because of this assumption, everywhere the thermal conductivity of all the fins will be constant K everywhere. Assumption number 5, uniform fluid properties, that is H is equal to constant everywhere. And the last assumption, but very important, insulated tip fin. That is, we are assuming there is no heat loss at the tip of the fin. This is the boundary condition we are supposed to consider. After schematic, after enlisting all the given parameters, after taking all the assumptions, let us enlist what you are supposed to find out. What we are supposed to find out? Heat transfer rate in case 1 and heat transfer rate in case 2. So let us do our calculations one by one. Now in this case, the individual fin is considered as insulated tip fin. And we are supposed to calculate heat transfer rate from single fin, and depending upon the number of fins, we will be calculating total heat transfer rate. So for insulated tip fin, the rate of heat transfer so first we need to calculate the rate of heat transfer from the single fin which is insulated at the tip. So for this you need not to remember, refer heat transfer data book. In my data book it is given in page number 50. In your data book it could be at page number 49 or 58. That depends upon the edition. Heat transfer data book by C.P. Kothandaraman. So you can calculate this Q as, I am directly writing this formula, H P K AC into Ts minus T infinity 10 of hyperbolic of ml. Okay. This is the formula given in the data book. You can refer. I can wait for 30 seconds. Now in this formula, someone raised this query in the previous lecture. This is the combined function of 10 hyperbolic. This is not the value of h, please mind well. This is called as hyperbolic 10. This is a trigonometric function actually, 10 hyperbolic. In your calculator it is given. So you have to take 10 hyperbolic of m into L value. So this formula is given in the data book. Now, if n number of fins are there, so Q total will be n into Q. That is n into square root of HP KAC into TS minus infinity 10 of hyperbolic ml. This is the equation what we are going to use for case 1 and case 2. Got the point? And in this equation, what is the value of m? It is nothing but HP over KAC. And its unit is per meter. So both these two formula we are going to use for our calculation. Got the point? Please refer data book. If I am saying refer page number 50 or 49 or 58, you will find this formula. There is a table, and for insulated tip fin, you can have this formula for heat transfer rate. Excuse me. Okay, now let us solve for case 1. What is case 1? N1 is 6 and L1 is 10 centimeter. So what will be Q1 in this case? Q1 will be N1 into H P K A C, because H perimeter K and cross sectional value is going to remain same for all the fins. TS minus infinity 10 of hyperbolic M1 L1. Let's say this is equation number 8. The rate of heat transfer for case 1 is N1 into square root of HP K A suffix C into TS minus infinity 10 of hyperbolic M1 L1. Now how to calculate this M1? It is nothing but HP over AC. Let me check correct values I have taken or not. So this parameter is also going to remain same. Okay, M1, because H is same for all the fins, P is same, K is same, AC is same. So M1 is equal to M2 is equal to M The value of H is 25, K is 250, AC is 2.5, and P is 5 centimeter. So in both the cases, HP is 25.05 over 250 into 2.5 into 10 to power minus 4. Please check whether I have put correct values or not. H is 25, K is 250, AC is 2.5 and 0.05. So what will be the value of this M? Can someone tell me? Please someone tell me this value. I could calculate this value as 4.472 per meter. Is it correct value?
Yes, sir.
Okay. So now we can calculate Q1. So it is 6 into the value of H is 25, perimeter is 0.05, K is 250, cross-sectional area is 2.5 into 10 to power minus 4. HPKAC, the value of TS is how much? 215. Ten of hyperbolic, value of M is 4.472 into the length L1 is 10, that is 0.10. See the value of, you can do the calculations. The value of M is M1 inverse and value of L, a unit of M is per meter and unit of L is meter. So this will become unitless. ML is actually unitless and we can take any tan or tan hyperbolic or sine hyperbolic of only unitless parameter. So this way you remember the unit. So after calculating this, I will get the value of Q1 as. Please check whether it is correct or not, what I have calculated. Answer number 1 for case. Please check because I do lot of calculation mistakes. Is it correct? Oh, this 6 is outside. That is again a mistake. It is not mistake, it is blunder. It is like this. 6 is number of fins. H, P, K, AC. Is it correct? Someone turn on the mic and tell me.
Yes, sir. It's correct, sir.
Okay. Then let us do for case 2. Case 2 is having, now we have increased the number of fins from 6 to 12, but at the same time we have reduced their length. Okay. So let us calculate Q2. It will be N2 into square root of HP KAC into Ts minus T infinity 10 of hyperbolic. M is same for both the cases because all the geometrical and surrounding properties are same. So M into L2. N2 is 12. Once again, let us put all the values. 25 into 0.05 into 250 into cross-sectional area is 2.5 into 10 to power minus 4. 200 minus 15. I am writing, okay, I have the facility to expand. So 10 of hyperbolic, the value of M is 4.472 and the length in the case 2 is 0.05. So from here, the value of Q2 will be 138.63 watt. Please check this answer. And how to calculate hyperbolic, that also I tell you. In your calculator, this hyperbolic function is there. So you need to press it. So after pressing this hyperbolic, you will get 1, 2, 3, 4, 5, 6 hyperbolic functions. So let's say I want to calculate 10 hyperbolic. So I have to press 3. So 10 hyperbolic will be appearing. Then 4.472 into 0.05 like this. Okay. I don't know whether you are able to see through my camera. Okay. Like this. 10 hyperbolic of 4.472 into 0.05 and this value will come out 0.219. Then multiply other terms. So it is correct, 138.63. Now this numerical is not a merely numerical. I can draw some conclusions because now in C, case 1 there were 6 fins of 10 centimeter length. In case 2 there were 12 fins of 5 centimeter length. So in second case, though we have reduced the length of the fins, but their numbers we have increased. So what conclusion I can draw from here? The length of the fin or increasing the length of the fin does not increase the heat transfer rate, basically. Isn't it? Short fin will be more effective if their numbers is more. So I can write here conclusion. Increasing the fin length has less effect on heat transfer rate. So this is the conclusion of this problem. One very important point I would like to remind you, we have discussed fin efficiency. So fin efficiency will be 100% if fin length is 0. That is no fin at all. See, it is something interesting observation. We want to attach fins to the base surface to increase the heat transfer rate. But to maintain the fin efficiency 100%, from the formula of fin efficiency, what is the outcome? Fin efficiency will be 100% if fin length is 0. That is no fin at all. So from that discussion and from this numerical, I can conclude it. In order to increase the heat transfer rate as well as fin efficiency, length is not going to be the criteria, design criteria. Engineer cannot say that if I want to enhance the heat transfer rate by attaching the fin, so I must increase its length. Length is never going to be parameter. This is important conclusion from fin efficiency and from this numerical. Okay. So with this, you can solve the numerical in this way.